Okay, shall we start? So here we have two types of wave mainly as we discussed in the class. So the first one is the mechanical wave. Okay, what is the meaning of mechanical wave? So it is the wave which require a medium for their propagation. So it require medium for their propagation. So like sound wave. Medium for propagation. So example we can tell sound wave. So without any other medium, the sound cannot travel, right? So sound need a medium like a solid, liquid or gases. Okay, and its velocity, second point you observe that. So keep open the book, page number 379 there. Their velocity depends on the elasticity and density of the medium. Okay, that means speed of that waves like sound wave. It depends on the elasticity and density of the medium. And the third point, their velocity is comparatively less. Okay, like sound waves and light waves, if you compare, no, light waves travels faster. Okay, and sound wave travels with a very lesser speed, 330 to 340 meter per second in air. So its velocity is comparatively less. And they may be longitudinal or transverse wave. Mechanical waves, it might be a longitudinal or it might be a transverse. Transverse. So examples here, we can tell water waves, sound waves, seismic waves, okay, these are the waves formed in the earth surface layers. Okay, so due to that earthquakes and all, the seismic wave it is. So these are the example for a mechanical wave. In opposite to that, there is an electromagnetic wave. Okay, the second category, electromagnetic wave, or we also call it as a non-mechanical. Okay, so these are the electromagnetic wave, doesn't require any medium, do not require medium. And their velocity depends on permeability and permittivity. So permeability and permittivity. So what does it mean? Permeability and permittivity means, see, it is an electromagnetic wave. As we know that electromagnetic wave, it is a transverse in nature like this. So one is an electric field and one is a magnetic field wave. Okay, so this is the magnetic field wave. So the ability of the medium to allow the magnetic field lines, we call it as a permeability. Suppose we have some air medium or in any other medium, water medium or any other material medium, which may not completely allow the magnetic field lines to pass through it. Okay, then such kind of mediums has a less permeability value. Okay, permeability means what? It is the ability. Can you see my video?
Yes, sir.
Yes, sir.
Yes, sir.
It is the ability of the medium to allow the magnetic field lines. That is called permeability. Permittivity means it is the ability of the medium to allow the electric field lines. So these electric field lines. So it depends mainly on these two. Okay. So in free space, permeability, we can call it as a permeability in free space mu naught and epsilon naught as a permittivity in free space. It has a constant values that you will study later. Okay. In second PU, you will study that. And one more point on the electromagnetic wave is their velocity is very high. Okay, it's not like the sound wave. It is like the like light wave. Okay, so light has a speed of 3 into 10 power 8. Correct, no? So even all the electromagnetic waves in the spectrum, you have studied that X-ray, UV ray, infrared, correct, no? Gamma ray, and radio waves, microwaves, even the visible light. So all are the electromagnetic waves only. Okay, all are traveling with a speed of 3 into 10 power 8 meter per second. So they have a very high velocity, very greater velocity it has. And they are transverse in nature only. Okay, they cannot be longitudinal, they're always transverse in nature. Transverse in nature. Examples. So these are all the example: X-ray, UV ray, infrared, gamma, radio, microwaves. Okay, these are all the example for that. Mechanical wave and electromagnetic wave. Okay, any doubts here?
No, sir. No, sir.
Electromagnetic. Electromagnetic we also called as a non-mechanical. Yes. Moving to next part. The meaning of longitudinal wave and transverse wave. Longitudinal waves. Yeah, you can see in your book there is a picture. Okay, so in the longitudinal waves, it forms like a compression and rarefaction. I can show you in a different color. See, this is the compression zones. So compression zone has a high molecular density, so it has a greater pressure there. So these are all the compression region and rarefactions. So very few molecules will be there. The pressure is less here. This is the rarefaction region. So any waves moves in this form, like compression and rarefaction. I have given an example, I think, the compressed spring when it is released. When you compressed, the potential energy stored in it will be greater. And when you released it, okay, so it get expanded and it takes little moment. That potential energy converted as a kinetic energy, correct? No? So this is the compression, rarefaction, compression, rarefaction. So like this, the wave goes. Okay. The example you can tell that sound wave. Sound waves are the best example for this. Longitudinal waves. And whereas in the transverse, it goes like crust and trough. Transverse waves like this. So any waves which takes of this form, crust and trough, are called transverse wave. This is a crust and trough. The distance between two successive compression or here also. See, distance between the two successive compression or rarefaction we called as a wavelength. Even in the case of transverse also, distance between the compression, crust or the trough, we call it as a lambda. That is a wavelength. So what is a transverse waves? The transverse waves or the waves goes perpendicular to the direction of propagation. See, this is the direction of propagation here. So here the wave or the particle moving perpendicular to it. But here in the case of longitudinal, it is going parallel to the direction of propagation, or you can say along the direction of propagation. Okay. For the transverse wave, you can give an example, light waves or electromagnetic waves. These are the example for transverse waves. Yeah, just turn the page. You can see there the difference between the longitudinal and transverse wave. Longitudinal and transverse wave. Just check it. The first point in the longitudinal, the particles of the medium vibrate parallel to the direction of propagation. Okay. But whereas in the case of transverse, it vibrates perpendicular to the direction of propagation, like this, perpendicularly to the direction, means this is the x-axis for this. And here they propagate by creating series of alternate rarefaction and compressions. Correct, no? So compression, rarefaction will be there alternatively. But here crust and troughs will be there. And here it can travel through solids, the third point, liquids and gases. It can pass through all other medium. Here they can travel in solids only or in the surface of water, they given. Which one? Transverse wave. Transverse wave, they can travel in solids only. Actually, here it can travel through gases also. Okay, transverse waves are, kind of a non-mechanical. So just make a correction there. It can pass through in all the mediums. Even it can pass through in vacuum also, you can tell. It can pass through in vacuum also. Just make it correct. Next, medium must possess bulk modulus for the propagation of these waves. Okay, longitudinal. So medium must possess bulk modulus. I think you are not aware about this concept because this concept comes in the mechanical properties of solids. Bulk modulus, rigidity modulus, and Young's modulus. The meaning of bulk modulus is it is a ratio of change in volume to the original volume of the medium. Change in volume to the original volume of the medium. So here the medium must possess this kind of change. Got it? The volume must change. It should not be a rigid medium. Got it? Here, in the case of transverse wave, it must possess shear modulus. The meaning of shear modulus is that we also call it as a rigidity modulus. Rigidity modulus. So it is sharing stress by sharing strain. Sharing stress divided by sharing strain. So again, this concept comes under mechanical properties of solids. You will study there in detail. Okay. So just know the fact. So here it must possess shear modulus. Here the medium must possess bulk modulus. And they can't be polarized. First one, they cannot be polarized, but here it can be polarized. What is the meaning of polarize? Anybody knows the answer? Polarize meaning? They can't be polarized. Here they can be polarized. The polarization is nothing but is a filtering the intensity of that wave. Okay. If you want to reduce the intensity of that wave, that phenomena we call as a polarization. Here sound waves cannot go polarization. It never, it never support for such kind of phenomena. But the light waves, it has a two kinds of vibration, right? Electromagnetic wave, electric field also there, magnetic field also there. And electric field vectors possess two kinds of vibration. Okay. So in that, a particular vibration can be restricted, that can be filtered. Like how you see the sunlight through the sunglasses. When you see the sunlight through the sunglasses, you won't feel that much of high intensity light, correct? Because sunglasses filters the light rays. So that phenomenon is called polarization. So this can be polarized, but not the sound waves. Okay, longitudinal waves cannot be polarized. Okay, just go through it once and just write it down. Write it down now itself. Longitudinal waves and transverse wave, very important 3-mark question it is. Yes, complete it in 2 minutes. Complete it. Okay, next one is an angular wave number. So just go through once again. Amplitude, it is a maximum displacement traveled by the particle. Okay. Time period, time taken to complete one full oscillation. Frequency is the reciprocal of time period, or we can also say that is the number of oscillations made per second. Angular frequency, it is the 2 pi times the number of oscillation made in 1 second. SI unit is radian per second. And wave velocity, it is a distance traveled by the wave in 1 second. In 1 second, how far it traveled from the origin. So that is called the wave velocity. And wavelength, distance between the two successive crusts or trough, we call it as a wavelength. And the next definition, angular wave number. Angular wave number denoted with the symbol K. So it has a formula that K is equal to 2 pi by lambda. It is a 2 pi times the number of waves per unit length. Okay, per unit length. Can consider here. That means per unit distance also you can say. Or between the two successive crust and trough. Okay, that is the lambda. No? So it is a 2 pi times the number of waves covered per unit length. Per unit length, how much distance, how many waves are completed. That must be 2 pi times. 2 pi times means one full wave. So the SI unit becomes radian per meter. So these are the highlighted definitions in this chapter. So just mark it. And now next we have relationship between wave velocity, frequency and wavelength. Okay. The velocity of the wave is nothing but distance traveled by time taken. That distance we can take it as a lambda. Okay. That's a wavelength divided by time period. So velocity is equal to 1 by time period. We know that it is a frequency. So we can simply write as a V is equal to F lambda. So where V is the velocity of the wave and F is the frequency and lambda is the wavelength. The relationship between wave velocity, frequency and wavelength. As it keep propagating in one direction, it's keep on completing, one full cycle. That is time period, correct now? And it covers the wavelength also. For a particular distances, it covers complete one wavelength. And it is traveling with some velocity v. So this is the relationship between wave velocity, frequency and lambda. Yes. Next, the most important question is to find out the displacement equation. Displacement equation of progressive wave. Progressive wave. Progressive wave means these are not a stationary wave. It is keep propagating in one direction. So this is the diagram you can see there. Correct. Drawn one wave there. And this is the origin. Here is a y component and here is the x component. And this is the direction of propagation. It is traveling with velocity v. And let us take a particular point P here. It is at the distance of x. And this will be the wavelength lambda. So one full wave, it completes the wavelength lambda. Okay, till here. Now the displacement of the particle at x equal to 0. Displacement of the particle at x equal to 0 means at the origin. At x is equal to 0 at time t. So how you can express this? So I'm taking the condition, the position is 0 and the time is t. The displacement, I'm denoting with the symbol y. So as we know the wave equation, you can write in this format, y is equal to a sine omega t. So where a is the amplitude, omega is the angular frequency. Next, let P be a point at a distance x from O. This is the point P. You can see that the point P is there at a distance of x. Since the disturbance is traveling with the speed v, therefore it will take time, okay, for reaching the particle position P here. So it takes the time of t is equal to x by v, right? So hence the next equation we can write it as a x comma t is equal to y, x is equal to 0, t minus x by v. And the same I explained in the class also, the t minus x by v. So this is the x by v position. Here is a t minus x by v, it becomes. Therefore, y of x comma t is equal to, we can write it as a sine omega t minus x by v. The initially it was only omega t, now it is omega t minus x by v. Now just multiply the omega, get omega t minus omega x by v. So that is equal to a sine omega t minus kx. So where k is the omega divided by v. This is the k. So this can be the displacement equation. So this is the standard equation for the displacement. So very important derivation it is. See here, the wave is propagating along positive x-axis. It is moving along positive x-axis. Suppose if it is moving along negative x direction, this is the wave going along positive x. If it's moving along negative x direction, under the node, we can see the point there, the first point under the node, okay? Along negative x-axis, along negative x-axis, y is equal to a sine omega t plus kx. Since the direction is opposite, it becomes plus kx here. And k is what? Omega by v, as we know here. So omega is 2 pi f. V we can write it as a f lambda. So ff will be cancelled. So we get the k value as a 2 pi by lambda. This is the definition for a wave number. Just now we saw this. K is 2 pi by lambda. Correct, no? 2 pi times the waves completed per unit length. Now by using that standard equation, we can get a different forms of equation for the progressive wave. the different forms of progressive wave equation. Different forms. The first one, see, we know that y is equal to a sine omega t minus kx. I'm taking the example for wave moving along positive x direction. Okay. So, and this can be written as a y is equal to a sine omega. So, if you can take a omega common here, I can write it as a t minus kx by omega. Okay. That can be further written as a sine omega t minus x by b. Because what is the reason? The reason is k, we can write it as a omega by b. So in the place of k, you can replace omega by b, then omega omega will be cancelled. You get t minus x by b. And as we know, omega is 2 pi f. You can write in the place of omega 2 pi f t minus x by b. And further, you can also write like this, a sine 2 pi. Just multiply this f value inside. So we can write it as a ft minus fx divided by b. Okay. So it will be a into sine 2 pi. Frequency is the reciprocal of the time period. And here fx, v can be written as a f lambda. Ff will be cancelled. Therefore, y will be a sine 2 pi t by t minus x by lambda. This is the another form in terms of time period and in terms of the wavelength. Also, we can write as a y is equal to a sine 2 pi by lambda. 2 pi by lambda, if you take common, what do you get here? Vt minus x. See here, the lambda, if you want to take common, here also you need a lambda, correct? So you can multiply and divide with the lambda there. Then you will get the velocity. Okay, v is equal to f lambda. So with the help of that, you will get this equation vt minus x. So these are the different forms of the displacement equation when the wave is propagating along positive x direction. As just I'll give you a time now for 2 minutes. Just complete it. Complete this derivation, displacement equation, and then different forms of the wave equation. Yeah, completed. Yeah. Java Sharif, yes, along the x direction. The wave is looking like along the x direction, Javad, but the particle is vibrating perpendicular to the x direction. Okay. Since the particle is perpendicular to the vibration propagation, hence we are taken sine here. Okay. See, everywhere you are using the particle vibration perpendicular to the mean position only, means along the x-axis. Perpendicular to the x-axis only the vibration we are taking. Completed, yes. There are a lot of messages and I cannot scroll here. Yes, finished. Okay. Yes, Akshay. Yeah, you can unmute Akshay.
ನೆಕ್ಸ್ಟ್ ಸ್ಲೈಡ್ ಅಲ್ಲಿ ಇದು ಮಾಡಿದಾರೆ ಸರ್ ಒಂದು ಚಿಕ್ಕ ಡೆರಿವೇಶನ್ ತರ ಅದರಲ್ಲಿ ಸ್ವಲ್ಪ ಡೌಟ್ ಇತ್ತು.
ಹೇಳಪ್ಪ.
ಇದಲ್ಲ ಸರ್ ಅದು ನೆಕ್ಸ್ಟ್ ಇದು ಮಾಡಿದ್ರಲ್ಲ a sin 2 pi t by capital T minus x by lambda.
ಇದಾ?
ಇದರಲ್ಲಿ ನನಗೆ ಅದೇ ಇದರಲ್ಲಿ ನನಗೆ ಏನು ಗೊತ್ತಾಗ್ಲಿಲ್ಲ ಅಂದ್ರೆ
here I replace the v as a f lambda.
Okay,
and f I taken as a 1 over t here. This first term f I taken as a 1 by t time period, no?
sir.
So here f I kept as is, f and f get cancelled, x by lambda is there.
Yes sir, correct.
Yes.
Square body.
Yes, next. Relationship between phase difference and path difference. Okay, that's the next one. Relationship between phase difference and path difference. Even it is also proved, but I will explain once again. What is the relationship? See, as we know that the wave equation, so at the position x and after time t, okay, so we can write it as a sine omega t minus kx along the positive x direction. I'm taking the standard equation. So at the phase is nothing but what? The state of vibration. Correct, no? Phase means state of vibration. So that phase is denoted by this term, phi. We can call it as a phi. Okay. So here the phase phi can be written as a omega t minus kx. Just call it as equation 1. Now let's consider two particles at two positions. We are considering two particles at two different positions. Two different positions. What are the positions? So let it be the x1 and another be the x2. x1 and x2 are the positions. For this, okay, they have different phases, right, for the different position. So at the same time, the phase of these two particles can be written as a phi 1 omega t minus kx1. Here I'm taking at same time t. At same time t. So omega never changes, k value never changes. Phi 2 omega t minus kx2. This is for a two different particle. I'm getting the two different phases. So here, if the particle second particle is having a greater distance than the first particle. So here if x2 become greater than a x1, then here obviously the phi1 value will decrease. The phi1 value will, see the x1 is lesser, no here. If you give the less value to the x1 and greater value to the x2, then phi1 value will be greater than the phi2. Therefore, the phase difference can be written as a delta phi is equal to phi1 minus phi2. Are you understanding? I am taking the same example here with the two different particles. Okay, let us consider one particle is at the distance of x1 and another particle is at the distance x2. I am taking here x2 particle here and I am taking here x1 particle. Okay, observe the distance x2 is greater than compared to the x1. So the particle which covers the more distance having the less phase. Okay, that means less state of vibration it has. Okay, so that difference I can find out here. Phi1 minus phi2, omega t minus kx1 minus of omega t minus kx2. Now multiply the negative sign. So omega t will be cancelled. Then we get kx2 minus into minus become plus kx2 minus kx1. So I'm taking the k common, x2 minus x1. So this x2 minus x1 can be called as a path difference. So I can just write it as a delta x for that. Okay. So what is the reason? Since path difference is delta x, x2 minus x1. Yes, of course, there is a path difference. The particle x2, particle meet at x2, it is having the longest path than compared to the first particle. The first particle covers a very short path from the origin. So that difference, what we have, that is called the path difference. So the formula is, what is the k value? And we know the k value also, right? K is wave number, that is 2 pi by lambda. Therefore, we can write it as a delta phi is equal to 2 pi by lambda into delta x. So phase difference is equal to 2 pi by lambda times the path difference. Okay, so very important. I'll explain you once again this. Yeah, just observe. We are going to derive the relationship between phase difference and the path difference. So phase difference means difference in the state of vibration of two particles. Path difference is difference in their positions. You can see here on the whiteboard. Okay, so this is the first particle position. Here is the second particle position. The second particle covered a large distance than compared to the first particle. Correct? Now that is a path difference. So generally, we denote the displacement equation with this equation for the positive x-axis. Correct? No, positive x-axis propagation omega t minus kx. Here, the angle omega t minus kx that defines the phase of that wave. Phase means state of vibration. Okay, phi is equal to omega t minus kx. Now, for two particles, we are considering for two particles at two different distances like x1 and x2. I can get the two different phases, phi1 and phi2. Here, the condition is that if x2 is greater than x1, then phi1 will be greater than phi2. You can check with the random values. Okay, if you subtract the lowest number, correct? No, see, take the x1 as a 2 and x2 as a 10. If you subtracting highest number, then the phase will be very less. If you subtracting the least number, then the phase value will be more. So phi1 will be greater. Then I want to find the phase difference here. delta phi phi 1 minus phi 2, substitute the values, take the k common, and here x2 minus x1 can be called as a path difference, that is defined as a delta x, and k value is 2 pi by lambda, that is a wave number. So we got the equation delta phi 2 pi by lambda into delta x. Okay, very important. Just copy it once. It's completed, students. I hope it is completed. Yes. Next one. Characteristics of progressive wave. Characteristics of progressive. Progressive means it is keep traveling. It is not a stationary. Progressive mechanical wave. So you already know about the mechanical wave properties. What is the progressive mechanical wave? The first property that the waves produced at any point in a medium propagated by continuous periodic oscillations of particles about their mean positions. Okay, so the particles keep propagating like this about their mean position. Continuously it keep moving. And the second, during wave propagation, there is a transfer of energy. Very important. There is a transfer of energy without any transfer of medium. Energy will transfer, but not the medium particles. Without any transfer of medium. Next, third point, the wave velocity depends on the elastic and inertial property of the medium. The wave velocity means V, it depends on the elasticity of the medium. Elasticity and inertial property means you can say density. Okay, inertial property of the medium. It is already mentioned in the mechanical wave properties list. Next, fourth point, every particle along the wave vibrates with same frequency and amplitude about their mean position, but the phase of the adjacent particle is different at given instant of time. Okay, suppose if I take a particle C or particle A and particle B, particle C. Okay, I'm taking a 3 particles here. So every particle along the wave vibrates with same frequency. Frequency will be same. How much the oscillations it produces or the vibration, it is same. And the amplitude about their mean position also same. But the phases are different. So this will be having a phase 1, this is the phase 2, and this is the phase 3. Okay, phases are different at that particular instant of time. Next, point number 5. The waves undergoes reflection like light. Okay, it undergoes reflection, refraction, interference, and diffraction. Interference and diffraction, but it doesn't undergo polarization. You already listed it. Doesn't undergo diffraction, undergo polarization. It undergoes only these major phenomena. Next, point number 6. The wave propagation is longitudinal inside the liquids and gases. and they can be transposed on the liquid surface and on the solids. Very most important point it is. The point number 6, okay? So like if you take a water surface, on a water surface, you can see the ripples like this, correct? No? This is a water surface. I'll take a beaker of water. But inside, what are the waves formed here? When you drop a stone, you can see the ripples only on the surface. But inside wave propagation is longitudinal. Inside it is longitudinal. Wave propagation can be transverse on the liquid surface. Here it is looking like transverse. You can see like it's going like a tides. Okay, in oceans or in beaches, you can see that crust and trough like it goes. It is on the surface. You see like transverse, but inside it is longitudinal, compression and rarefaction kind. Even it is true on a solids also. Next, relationship between wave velocity, wavelength and frequency. We already know V is equal to F lambda. And the point number 8, the frequency of wave doesn't change when it goes from one medium to another, but wave velocity and wavelength changes. That means frequency remains constant. Remains constant. Okay. If the wave coming from air to water, see from air to water, if it is entering, the frequency never changes. Might be its velocity decreased or wavelength may changed, but not the frequency. Frequency of the wave, that means for a mechanical it is. Okay. So when the mechanical waves are in motion, so the frequency never changes when it travels from one medium to any other medium. It's not in the same medium. Any other medium or in a same medium also the frequency is same. And even if it changes the medium also, the frequency remains same. The point number 9, longitudinal waves do not show polarization. Yes, this one we already listed. Okay. Do not undergo polarization. Whereas transverse waves undergo polarization. Okay, this is for longitudinal. And for a transverse, it is undergoes polarization. Yeah, out of this, you must know any 5 properties, very, very important. One is asking, sir, is energy lost during transfer of energy? Yes. Okay. So as it keep transferring, see here, this is the first circle. You can see here is a greater energy. For the next circle, it transfers. And for the next circle, it transfers. Okay. So all the energy keep distributing from particle to particle. Okay. So here what happens? The phase keep decreases. Phase means the state of vibration of the particle keep decreases and energy also keep decreases. Phase difference and part difference. How many marks, Chandana? 3 mark. Mayank didn't understand the 6th point. Mayank, inside whatever the wave forms in the liquid, suppose when you drop the stone on the liquid, okay, on the surface of the liquid, you can see the ripples like this. That is a transverse in nature. But when the stone went inside, okay, here also there will be a wave, no, here also there will be a disturbance. So that is a longitudinal. It goes like compression and rarefaction inside. Next. Mayank, understood? Yes, yes. Okay. Nitya. Move to previous page. Yes. Here the 4th point is important. 4th point also very important here. Phase of the particles. will be varied. I hope you understood in today's class what are the contents we have covered. Okay, once again, let's glance from the beginning. Yes, I started from the difference of the mechanical wave and the non-mechanical electromagnetic waves. So differences, and then difference between the longitudinal wave and transverse wave. And important definitions like amplitude, time period, frequency, angular frequency, wave velocities, wavelength, wave number, relationship between wave velocity, frequency, and the wavelength. And we derived the displacement equation. It is for 3 mark. And wave number equation, 2 pi by lambda, the proof that how we got it. And different forms of the wave equations. Very, very important, very useful while we are solving the numericals. And relationship between phase difference and the path difference. It's the most important question again. Characteristics of progressive mechanical wave. Okay. So simultaneously you have to complete in your notes. Okay. Keep writing the notes and complete all the previous chapter notes also. Here we have a lot of time now. So you can complete all other notes and complete your record also. Follow the instructions, what I given to write the record, complete all other works. Okay. Make use of your time and study them. And next class, I will continue with this. Okay. With the EPL. So we do speed of transverse wave in string and velocity of sound. So in the next class, we are discussing the EPL content. Yes, bye all of you.